somebody?
Well, in any case, it's going to be recorded, so it should be in English.
Yeah.
Okay. Okay.
No problem. Okay. So I see that maybe the number of participants is stabilizing. So we can start. So it's good afternoon to everybody, and welcome to this today MOX colloquium. It's a great pleasure, and I'm very, very happy to introduce the speaker of today is Professor Ricardo Nochetto from University of Maryland. Certainly, Ricardo doesn't need any introduction because he's a renowned and very well-known worldwide expert in numerical approximation of partial differential equations. However, I would like to spend a few words to introduce Ricardo, especially for the youngest part of the audience. Maybe doesn't know Ricardo very well, I doubt, but Ricardo got his PhD in Buenos Aires in 1983. Then he moved as a postdoc to Pavia and at Istituto of Analisi Numerica, and stay in Pavia for 3 years. Then he moved to Minneapolis, and then in 1987 he joined University of Maryland, where he's actually professor of numerical analysis. Ricardo worked on several different topics, and every time he got in very relevant results and gave very important contributions, and ranging from numerical approximation of nonlinear PDEs, free boundary problems, geometric and fully nonlinear PDEs, to fractional diffusion and basic theory and application of finite elements. And here I want to mention, for instance, the contributions to the understanding of optimality and convergent properties of adaptive finite elements. Among several different awards that Ricardo received, I just want to mention that Ricardo was invited speaker at the International Congress of Mathematicians in 2010, and then also plenary speaker at ICIAM in 2015 in China. He's also Scion Fellow and AMS Fellow. But now it's time to leave the word to Ricardo. So please, Ricardo, we are very excited to hear from you and the recent results on fractional diffusions, regularity, and approximation. Please, Ricardo, the floor is virtually yours.
Virtually mine. Thank you, Marco, and thanks everybody for listening. It's a pleasure to be talking to you and giving this lecture. Disclaimer, I mean, you know, for me, 9 in the morning is still too early. I'm not an early bird, so my brain is barely functioning at this point. And Marco knows because we have Zoom calls in the morning, not this early. So the purpose of the talk is to give you sort of a survey of fractional diffusion, several aspects of it. So here is the outline of the talk. And I like to spend, so the talk sort of centers around these two issues, regularity on one side and approximation on the other. And as you know, they are, you know, different sides of the same coin. So I like to relate them. So I spend most of the time in the linear part, which is this first 4 topics, and then I will say a few things about quasi-linear approximation towards the end. Okay, so let me first motivate the reason for fractional diffusion. So this is a cartoon of something well known that leads to the usual diffusion, where we have a random walk of a particle along a line. So the line, we are in 1D, say we scale the integers by h, so the spacing now is h, and these are possible states of a particle, and use the probability of a particle to be at a position x in this lattice at time t, which is also, you know, a scale of the naturals. The tau is the time step. So the probability of a particle to be at this point, x at time t plus tau, depends on the probability. So with, you know, weights 1/2, probability 1/2 to be on the left or on the right and jump to this point. So by rearranging these equations, subtracting u to both sides, you see that we get, excuse me, we get this equation here, and I subtracted u to both sides, and then I divide it by tau on one side and h squared on the other, because I'm relating them in the usual way, in the diffusion way, 2 tau equal h squared. So this is something well known. When we take the limit of h and tau going to 0, satisfying this relation, we end up with a heat equation in one dimension. And so what happens when we allow the particles to see beyond the next neighbor? Okay, so we allow jumps. And then we associate with jumps a certain probability, which is called here capital K. So basically, again, the idea is that the probability of a particle being here at a certain point, x at time t plus delta plus tau, depends on, you know, probabilities which are measured by this kappa of the particle being at other positions, k plus h k at time t. So this equation here simply generalizes this next neighbor equation. And of course, we know, because kappa k is a probability, that the sum over all the intervals is 1. So rearranging this equation, subtracting, as I did before here, u at xt, and using the fact that the sum of the k's is 1, so I can put the u on the other side, we can play the same game that I did before, except that now I need to be specific about the model, and I'm going to say that this k, that depends on little k, is going to behave like this, with a certain constant, appropriate constant here in front, which is not relevant for what I'm saying. And so by putting it in and associating tau and h in this fractional diffusion way, when s is a real between 0 and 1, we end up with this equation in the limit. This is an integral equation, which is the fractional heat equation in 1D. Of course, when the problem is stationary, so there is no time dependence, we simply get the fractional Laplacian, which is the topic of this talk. Okay, here you see a number of references, mostly applications, because this is a type of topic that found applications in many, many areas. You see early applications in elasticity to anomalous diffusion, more recent on peridynamics, and many applications on fracture, and you name it, porous media, certainly applications in finance and material sciences and image processing. And it goes even into fluid dynamics. You see Navier-Stokes, quasi-isotrophic equations, Cahn-Hilliard phase transitions, and the list goes on and on. I want to make a point here, just very quick, that these two names, Caffarelli and Silvestre, are important, as it happens with Caffarelli in many other areas of nonlinear PDEs, because they came up with an extension in 2007, the so-called Dirichlet to Neumann map, that opened the window of PDE theory to understand these integral equations. This is a very influential contribution, as you can see, just one single paper, a number of citations. And it created a motion that continues today in the PDE world about regularity and of various types of nonlinear fractional diffusion equations, and also, you know, in a sense, motivated many applications. This is just a partial list. Okay, so let me now move into the specific topic, which is the formulation of the fractional Laplacian. I'm going to be dealing with bounded domains. And so the domain omega will be open and Lipschitz bounded in any dimension. D will stand for the dimension, and the right-hand side, let's say, take it in L2, at least. So the equation that is written here is the equation in Rn, except that we are going to assume that the function u vanishes outside the domain omega, which has still a probabilistic interpretation in the sense that the particles that are described by this probability will be jumping, and if they happen to jump outside the domain omega, then the process will be killed, and then the probability will be 0, and that's it. Process stops. That's the interpretation. But the problem still is a problem formulated in Rn, except that, again, I'm saying that u is 0 outside the domain. So this is the the integral representation, you see the domain is Rn, U again is 0 outside omega. But of course, there are interactions between the domain and outside the domain. This constant, which is explicit here, makes this definition consistent, in fact, the same as when we use Fourier transform, which will play no role in this discussion. Because of this structure here in red, the natural space and the natural norm, let's say, is induced by this scalar product, which is the usual scalar product in HS in Rn. But since the functions that we are dealing with are bounded at 0 outside the domain omega, then the space is called HS tilde. This is a standard notation in PDEs. So again, this parenthesis with the subscript S stands for this semi-norm, which happens to be a norm because I'm taking functions to be 0 outside omega, and then Poincaré inequality holds, and this the induced norm is 1 bar with a little s as a subscript. Okay, so this is the natural space where this problem is formulated. So here I again wrote the bilinear form with a scaling factor such so that the problem is consistent with the Fourier definition, which you see here. Okay, this is just the purpose of this constant that we can ignore from now on. The problem is symmetric, as you can see, happens to be continuous and coercive in this space, just because we are dealing with the norm of the space, basically. And so this fact is enough to formulate the problem as a variational problem and apply Lax-Milgram. So the existence and uniqueness of this is well known with the function f, right-hand side of the problem. Here, the forcing in the dual space of H S tilde. So the issue is not the formulation, it's about how the problem looks like, and this is, or how the solution looks like, and this is where the first important point I want to make is. So it's about regularity of solutions. Regularity of solutions, as I said, they are one side of a coin because they impact on what we can say and do from an approximation point of view. There are classical results, as you can see, going to the 60s, and more recent by group, saying that there is a limit of regularity. No matter what the domain can be as smooth as you like. It's infinity. The solution happens to have a limit of regularity that has to do with the boundary behavior. This has been improved recently. Regularity of the boundary has been improved recently to C1 plus beta by group and Abels. But the regularity basically is like this. The solution can never be better than HS plus 1/2 minus something. Okay? And the behavior, this limitation in regularity, no matter how smooth F is and how smooth the domain is very different from the classical problem. And this is not because of lack of tools or poor tools. There is an example here. It's basically the only example that we know, explicit example on a ball, that you can construct an explicit solution radially symmetric, right-hand side equal to 1, so smooth, and right-hand side as smooth as you like. The solution behaves like a distance to the boundary to the power s. This function is not in HS plus 1/2, so this is the sharp regularity, and this is what has been proved. Okay? There are other techniques, for instance, by Rosoton and Serra, that measure regularity in Helder spaces by introducing weights. The weights here, this delta is the distance to the boundary, so by introducing weights, you can gain differentiability. I will come back to this. However, these results require an exterior ball condition. An exterior ball condition is okay from the PD point of view, but if you think about dealing with polygonal domains, as we use with finite elements, with approximations or problems in general, an exterior ball condition implies convexity. And so this is a limitation that will come up. Okay. Exploiting these ideas, this Helder regularity, is possible to do estimates in weighted Sobolev spaces. And here you see some of that. So you introduce a proper weight, and if you introduce a proper weight, you can get differentiability. You can add something here. And in fact, the result is proved by Acosta and Bortagaray is this. You introduce a weight of order 1/2, and then you get 1/2 differentiability. Remember, before this was 1/2 plus S, now you have 1 plus S. Okay, and this is based on Rosoton and Serra. This is important because we converted this Helder estimate in something based on Sobolev spaces, which is useful for the analysis of finite elements, as you will see in a few minutes. Okay, let me now turn into something new that I wanted to explain a little bit better. It's a joint result with Mortagaray that was inspired by all results by Savare that turned out to be quite suited, at least the technique, quite suited for this framework. And these are regularity results in best of spaces that can be converted in Sobolev spaces, and so useful for finite elements. They are valid in Lipschitz domains, so there is no exterior ball condition. And the technique is very different from the usual regularity theory. This is more of a functional analysis approach to regularity. And you see the result here. If S, which is this fractional exponent of the Laplacian, is bigger than 1/2 and less than 1, then the solution is in this Bezo space with differentiability S plus 1/2, as we saw before for H, for the Sobolev space. This dot here means that the functions are 0 outside the domain omega. Integrability 2, and the third parameter infinity. Okay, and you have this estimate. You can view this as the estimate in HS plus 1/2 minus epsilon that I mentioned earlier, but without any regularity beyond Lipschitz. If S, the fractional exponent, is less or equal to 1/2, then you get this result. You get a pickup regularity of S. So you go from regularity S to regularity 2S, okay, in the same L2 base integrability. So what is behind this result? I wanted to say a couple of words. This is, well, first it's important because we're dealing with Lipschitz domains, so it applies to polygonal domains, for instance. The right-hand side is just L2. So this is very useful to do L2 estimates because they require duality, and you need shift theorems with right-hand side in L2. All the previous results have right-hand side that are much stronger, and so they are not good for duality arguments. Okay, what is it behind? So here is a very quick explanation of what's behind. In fact, the solution of our Laplace operator, fractional Laplacians, minimizes this functional, F2 minus F1, okay? F2 is the quadratic part, the HS norm, minus the linear part. So by dealing with these two functionals, if I can extract some regularity from these two functionals that depend on quadratically or linearly in V, then we can get information about the function, regularity of the function, and you will see how. So for the moment, let's focus on this F1 and F2. So the first thing is to create a translation, okay? TH stands for a translation. So I get the function V, I translate it, as you see by H. H here is just a vector of size bounded by rho in RD. But I do this translation locally. So I use a function phi, which is a cutoff function. As you see, the function is 1 in a ball, B rho, and 0 outside the ball of radius 2 rho. So outside the ball phi is 0, okay, and then you get that this TH of V coincides with V. Inside the ball of radius rho, then there is a usual translation. Okay, so this is an obvious estimate. It works as a translation. The function minus the translation is bounded by the size of a translation times to a corresponding power times the base of norm with differentiability sigma, which is the same as here. Now, here is the key. These functionals, the F1, which is linear, and the F2, which is quadratic, have some regularity in the sense that you evaluate the functionals on V minus the translation of V, both of them, and you divide by a power of H, because you see the V stands here and here, then you can relate this in terms of regularity of V. And here are the precise results. This is kind of obvious because it's linear. F1 is linear. This is less obvious and it requires some work, particularly because this is a non-local norm. Okay, so you see, if we have a regularity sigma, differentiability sigma, we can get here that these two quantities are close as h to the sigma. So that implies some regularity of the functional f. Okay, so now why is this useful? Essentially because, as you see here, if you are at the minimum, the solution of the problem is the minimizer of this functional, then you have this relation. So the HS norm for u minus any function in this space HS tilde is just given by the difference of the functionals. So now if I take this V to be a translation of u, and I know how this relate, V minus the translation and so on, I can say something about V minus the translation of it. So you define this modulus of regularity of the functionals, which, because of what I said before, this will be the modulus of regularity, are bounded by this regularity of the function V, this in red. So this is just rewriting what I said before, okay? So you see that these functionals are regular relative to the regularity of the function. So by going back to this formula here, I simply can say that the difference between u and a translation is controlled by this modulus of regularity times h to the power sigma. So now let's play the following games. We know when we start that u is in HS. So sigma, I can take sigma already to be s, okay? And by taking sigma already to be s, I can put this in the denominator, I get that this is bounded. But this controls now, by iterating the definition of Besov norms, by the reiteration theorem, you see here we have the norm HS, and because we are taking a difference and dividing by h to the s, notice that here there is a square. This is like an estimate for regularity s plus 1/2 plus s over 2. So we were able to increase the regularity that we knew originally, regularity s to regularity 3s over 2, just in one shot. Once you have this additional regularity, you can now say, okay, but now I know better. So I can reiterate, I can repeat this statement, and by iteration or bootstrapping, you get the result that I mentioned earlier. Okay, so this is a functional analysis approach to regularity that eventually leads to, by iteration, maybe finite or sometimes infinite number of iterations, you need to repeat. Here you need only finite number of iterations, here you need an infinite number of iterations, and these are the results, which are sharp. Okay, having said this, let me now move into the finite element method. Let me go quickly over this. So this is the standard setting. I have a mesh which I call tau h, finite element method. The mesh will be shaped regular, of course, not necessarily uniform or quasi-uniform. The finite element method will be of continuous piecewise linears, and this is important in many respects. The discrete problem is just written here. I'm restricting everything to the discrete space. And I want to quickly review 3 issues that are important in this setting. One is the matrix assembly, then compression, and then solution or solvability. The first about assembling the problem. You see, if we call phi the basis functions of our finite element space, the hat functions, basically we need to compute the stiffness matrix is the coefficients ai, j are the interactions of functions phi and phi j. These functions will interact, you see here the formula, whether they are close or not. So they can be far away, they will still have interactions. So this matrix is dense. There is another problem, which is that the fact that the kernel is singular, so it's non-integral. What you see is beyond, I'm in 2 dimensions in what I'm explaining, 2D. So this is the limit for integrability, and we are beyond the limit of integrability. So this is a singular kernel. So the implementation of this is very non-trivial. And even though there are techniques coming from boundary element methods, it took a while. As you see, people were doing computations in 1D until these people came up with the first MATLAB implementation of this using techniques from boundary element methods. After that, there were improvements, you see several of them, even to 3D. There is some more recent development by the group of Mario Bebbendorf, and very, very recent results in progress about exploiting the fact that the functions are piecewise linear and continuous to change the point of view in implementation, and that will work for any dimension bigger or equal to, in particular 3. This is something in progress. Okay, what about the fact that the metrics are dense? As I said before, there is interaction between basis functions no matter how far they are. In order to compress the functions, so to set elements to 0 if they are small enough, there are techniques like H matrices. These hierarchical matrices come to play, and instead of having complexity, which is a power of the number of elements, or the number of the dimension of the system, you get a log linear complexity. This is very technical, and I have not been involved, and you see a few names here of people that have worked on this in the last few years. Compression is important because otherwise you get dense matrices, and in this way the matrices are sparse, with a very complicated structure, but sparse. Now let me say a couple of words about fast solvers, and here is something I've been involved, so I want to describe it in a little more detail. And it's about BPX, so it's about additive multi-level preconditioning. So the idea that I'm going to describe is based on two properties. One is the space decomposition. This is classical, what I'm saying. The space can be decomposed as a sum of spaces, BJs. In each of them, you introduce some kind of smoothing called BJ and a corresponding norm. And then that induces an additive preconditioner that you get by composition of the L2 projection, this smoother BJ, and the injection from BJ into the full space. So in order to estimate the condition number of B, the preconditioner times A, which is written here, you need to have two properties. One is a stable decomposition of the space, which is written in this statement here. Given a function V, you can decompose it into VJs in each of the capital VJs such that the sum is V. And the scale norms are bounded by the norm in the space. That gives you, with the C naught, that gives you a lower bound for the minimal eigenvalue. And then boundedness, if you sum VJ in every VJ, this norm, which is a scale L2 norm, can be bounded by, this norm, which is the norm in the space, is bounded by the scales L2 norms with a constant C1, and this C1 bounds the maximal eigenvalue. So if you have these two properties, these constants give you a bound for the condition number. So we want to use this very general framework in the context of fractional diffusion. But fractional diffusion has two aspects of it, which is important to realize. We would like to have a preconditioner that is optimal, that you get, in a sense here in this formula, you get something that is independent of the number of spaces, okay? So independent of the mesh size. It would be, you will get a universal condition number. And that's something that has been achieved. The new feature here is that there is another parameter that enters, which is S, the fractional exponent of the Laplacian. And so you want to be uniform not only with respect to the level of resolution H, but also with respect to the fractional order S. And it turns out that you need the S uniform decomposition written here in terms of L2 projections. When you have a scaling here, this is the typical scaling for the HS norm. You can think of gamma as a power of 2, negative power of 2. And you see, this is sort of what you would expect in BPX theory, except that this is the natural thing for the highest level. Capital J is the finest level. But for the intermediate levels, there is a parameter, or actually a constant here, 1 minus gamma to the 2s, that when s goes to 0, and then the fractional Laplacian becomes the identity, becomes 0. Okay, this weights the intermediate spaces differently depending on s. And this minor modification is critical. Then you need some kind of S interpolation estimate, which is classical, and a local inverse estimate, which is maybe less classical because our spaces are non-local, and still we want a local inverse estimate. So you need to work a little bit. In any event, I show you here results. So what happens if you have uniform meshes or graded meshes? For S's that are small, you see 10 to the minus 1, 10 to the minus 2. When this parameter, this gamma tilde is a parameter, you can take this as a gamma tilde. It's a typo. I should have written here gamma tilde. It's something between 0 and 1. It can be 0, it can be, say, 1/2. If it is 0, it's not there, then you see sensitivity as the number of degrees of freedom grow, and also with respect to S. But no sensitivity at all if it is properly scaled. Okay? So this is a robust preconditioner in terms of resolution and fractional order. And here are the results. For the case of uniform meshes, the smoothing operators, which I call B bar, the bar is because you have uniform meshes, are here. These are the smoothing operators. You see it's the L2 norm scale with this power of the corresponding space Vj, and the factor that I mentioned earlier. And no scaling whatsoever for the finite space. And then this leads to this additive preconditioner, where you do what you should do more in general for the Laplacian, except that the intermediate scales are scaled with this factor. But when s goes to zero and makes this intermediate space less and less significant, as you would expect for the identity, because for the L2 norm, you don't need any preconditioner whatsoever. So with this, you get a result that tells you that the preconditioner, this B, leads to a uniform condition number, independent of J, capital J and S. Okay? And this is something that is, I mean, you can, let me go very quickly over this. You can see in this table, there is a robust behavior with respect to S and with respect to the level, so the resolution. If you have instead graded meshes by bisection, so you add a bisection every time, you get intermediate spaces, sort of Vj, but now they are not uniform anymore. They are, they are done by adaptivity, so they might be here and there of various levels of resolution. So how does this work now? Well, this is very technical. I'm not going to go into any details. The bottom line is that when you look at the finite space, which is this contribution, you don't scale it with any power of S, and the intermediate spaces you scale, as I said before. And then you have more or less the same idea of the preconditioner with this scaling factor for all the intermediate spaces, and not for the finite space. But here the scales in this finite space are not uniform, okay? They are done by a graded mesh. So again, you get uniform preconditioning. The result is technical. It requires several tools that have to do with the geometry of graded meshes done by bisection and so on. And again, this is a table showing that robustness that I talk about with respect to S and with respect to the level of resolution. So this is very, very robust. Okay, so let me move on the analytic part of the discussion of finite elements, which is error estimates. So let me first talk about global error estimates. So again, this is just repeating the setup. We remember we have a mesh tau h, finite element space, a discrete problem. And then we have a sort of best approximation result because our norm is the norm of the space. I'm using now a scaling equal to 1 to simplify my life. So the question is how well, this is the best approximation result, how well we can approximate U with piecewise linear elements, and the answer to that certainly depends on the regularity of U, which I mentioned earlier. In order to do this analysis, we had two things to do. We had to account for non-locality. This is a non-local norm, and the boundary behavior of U, which I alluded to earlier. Okay. Now, for quasi-uniform meshes, these are the results that can prove an early result here, assuming smooth domains, and a newer result, this one, using the best of regularity that I mentioned for any domains, Lipschitz. Okay, and notice that I'm only requiring here the right-hand side to be L2, and okay. All right. It turns out that the order 1/2, this order here that you see, can be also obtained for Lipschitz domains, not with the regularity theory that I mentioned earlier, but with the new results that I will mention towards the end. That's a result in progress. So you can read here 1/2 if you like, okay? But for Lipschitz domain instead of smooth domains. So these are new results. If you have graded meshes instead, graded in the sense that inside the domain we have a mesh size h, and as you move towards the boundary, the mesh decreases as a power of the distance, and near the boundary, the mesh is order h squared, h being the mesh size inside. With this, you go from half order to 1 order, up to a log, okay? So you get the linear order that you would expect. And in terms of degrees of freedom, you get the decay n to the minus a half. And you see this in computations. This is again the simplest and only example we have explicit. If you have uniform meshes, the decay is 1/2 for every s. And if you have gradient meshes, the decay is 1 for every s. Okay. However, there is a point here I'd like to make. When we talk about graded meshes, I'm saying that, you know, we had to go from a certain mesh size to a square of that mesh size near the boundary. And this is sort of in the spirit of Grisbar. Nobody said that you can construct these meshes, that you end up with some topological contradiction or obstruction. So we studied a constructive way to do this, which is based on a greedy algorithm, as you can see here. So you use the errors, the local errors in HS. Given a function u, I want to construct a mesh for which the interpolant of u does the best possible job, without saying a priori how the mesh is done. So you use a greedy algorithm, you mark elements for which you're given a tolerance delta, you mark elements for which this error is bigger than delta, and for as long as that happens, you keep refining. The algorithm stops, and when you stop, you get an optimal mesh with the optimal decay. Okay, but this is constructive. Okay, and as you see here, the result is quite recent. Okay, because our estimates L2, our best of estimates have L2 right-hand side, you can do duality arguments. And the duality arguments will now lead to error estimates in L2 much better than were known before. So here is the best of regularity that I mentioned that is useful to us with the right-hand side in L2, okay? This is a new result that I want to stress because it's important in this particular application. What is written here is the usual duality argument. So I need regularity of our adjoint problem. The phi is a solution of the adjoint problem. I need this type of regularity. And this type of regularity I can obtain in terms of a forcing for the auxiliary problem in L2. With that at hand, then we can get estimates in L2. You see for quasi-uniform meshes and for graded meshes that improve upon previous results. In particular, these results for uniform meshes or quasi-uniform meshes are sharp, according to a trick by Schatz that gives a lower bound for the L2 norm in terms of the H, in terms of the energy norm. Okay, the results are technical and the proofs are not complicated once you have the keys to have this regularity result. Okay. One thing that you realize is that the problem, as I mentioned, and I'm insisting on this, has a boundary behavior all along the boundary, not just at corners, that reduces the approximability. So one interesting question is what happens if you try to measure the error inside the domain, away from the boundary? Is the boundary behavior going to pollute the error inside, or the error inside behaves more like the interpolation error? And that leads to local estimates. So we know from PDE theory, the Cacciopoli estimate, that for harmonic functions says that if you have a harmonic function, you can control the gradient in half a ball in terms of the L2 norm in the whole ball. Of course, with the power here, or negative power of the radius of the ball, that makes this dimensionally correct. The proof of this is classically had to do with dealing with the cutoff function eta, and just simply using the cutoff function as a test function in the weak formulation. So you just use this cutoff function eta and you play a little bit, and then you get a bound for the gradient in half a ball in terms of the function L2 in the L2 error, the L2 function, the L2 norm in the ball. This is for the classical harmonic functions. And it's a natural question, what happens if you are dealing with the fractional Laplacian? Well, there is a result by Cozzi in 2017, which sort of extends this to S harmonic functions. Here is the result. You have the scaling that you would expect. Instead of R squared, you have R to the 2S. This is a natural scaling for HS that makes this dimensionally correct. And there is a term that has to do with the non-locality. These estimates that are purely estimates for integral equations, there is no PDE theory behind, it's just integral equations, can be converted, I mean, at least in a certain sense, the spirit of these estimates can be used to derive local error estimates. And again, this is a recent result. Now we are estimating the error in a ball inside the domain. Well, the ball doesn't have to be inside the domain. It can be even close to the boundary, but it's relevant when the ball is inside. In terms of interpolation error, as you can see in the entire ball, plus a global term, but in a weaker norm that had to do with the pollution effect. And the way this translates, there is a related result by using PDE techniques and the extension of Caffarelli-Silvestre. Ours is pure integral equation and technique. This translates into improved estimates. Here is a collection of results. It's not that important to read this table, but for quasi-uniform meshes, there is an improvement when you look local estimates that goes like this. You improve with order S or 1/2, the smallest of the two. And when you have graded meshes, there is an improvement like this, S or 1 minus S, the smallest of the two. Which means that when you move inside the domain, the boundary doesn't have such a bad effect. There is no pollution inside. And you basically get the approximation that you would expect from interpolation. This is good news. Okay. Now let me move into the last part of the talk, when I want to now abandon the linear regime and talk about quasi-linear equations. And I will show two of those, two types of equations. The first one had to do with perimeter. So it's well known, so it gives more Landau energy like this, when you see you have a double well potential, and you penalize variations with this gradient, that solutions minimizers of this problem when epsilon goes to 0 converge to characteristic functions of sets where the set E, say the limit, has a minimal perimeter. And this is a result by Modica some time ago. It's possible to modify this functional, and this has been done by these people, by introducing here a fractional norm, an HS norm in terms of the H1 norm. And it turns out that when S is between 0 and 1/2, because for S between 1/2 and 1, the limit of this coincides with the limit of this, with properly scaling of the functional. The limit of solutions of this have the sort of the same behavior. They converge to characteristics, and the boundaries of these sets satisfied. They have a minimal fractional perimeter. So let me be specific about what I mean in the simplest case of graphs. For graphs, in the classical case, we know that the surface area, which is written here, but the minimization of this would lead to surfaces with minimal perimeter or minimal area. So the sets under the curve, if this is the U, the sets under this curve, or you can think of a membrane, would have minimal perimeter. In the context of fractional diffusion, you can think the same way. So this is the domain of definition. You think now of the product omega times R. So you think of this domain in R d plus 1. And you think of the following situation. Given a function G outside the domain, this is a data. You want to find a function U connecting G outside, such that the subgraph, so the area below this, which I call E, okay, this is the set E here, will have minimal perimeter. So in other words, this surface here would have minimal S perimeter. And that means you are minimizing this functional here, where this quantity, this is a nonlinear function that extends this in the fractional case, and is written explicitly here. It turns out that if S goes to 1, this problem converges to that problem. So this is a fractional version of the minimal surface problem in the graph case. Okay, so if you now do a variation of this, first variation of this, then you get this problem where the first variation, I mean, you see the derivative of the first of the f before, and I'm dividing by the argument. The argument is this, so I can create the argument here. So this is the variational form. This is the bilinear form. As you can see, this is what I had before. This was a linear part, the fractional of a fractional Laplacian, and there is a contribution here now, very much that you have for minimal surfaces in graph formulation that makes the problem quasi-linear. The natural space where this is formulated is W2S1. Remember, S is less than 1/2. So here the differentiability is less than 1. So the functions that are written here do not have trace. So it's not clear what happens at the transition between U and G. There are no traces in this formulation. But the problem altogether is quasi-linear, degenerate diffusion, degenerate because of this. And the order that you can see here is S plus 1/2. Okay. What is a regularity? Well, you see the names of people involved in interior regularity. The solutions are infinity inside. But what happens at the boundary? At the boundary, it was discovered that the solutions exhibit a discontinuity for every S. Here, this is a problem in one dimension. The domain is -1, 1. Outside, G is -1 on this side, and is +1 on the other side. And you had to connect these two, and you see, let me show you a simulation where I'm going to be changing S. Here, S is very small, and it will be going from this value to 1/2. For 1/2, you will have the minimal surface. Okay? So I hope you can see it. This S is growing, and as S goes to 0.5, the solution goes from this, with discontinuities on the boundary, all the way, as you can see, the discontinuities tend to reduce to a straight line, which is a solution for the minimal surface in 1D. This can be repeated in 2 dimensions. So here there is an annulus, where what I'm changing is here I'm changing the height. And as we change the height, you can see the red part that corresponds to a transition within one element. So there is a discontinuity here. So this is called stickiness, and it happens. This is a universal behavior. It happens for every S. We are aware that these things happen for classical problems, but only in special circumstances. And here this is universal. This is the generic behavior. So here is a discretization. Again, the finite element space as before, our bilinear form, with I simply restrict to the finite element space. And the computation that I show you were done with the Newton method that we proved to be quadratically convergent. Okay, what are the properties of the discrete problem? Well, we have convergence of the energies. We have convergence of the solutions in a space slightly weaker than W to S. You see, R has to be smaller than S. We don't have error estimates. I mean, the regularity is quite bad, except when we deal with the geometric error, which is inspired by the classical case. You see the work by Fierro and Fesser for the classical case, where they came up with this notion of error that has to do with the normal to the graph. There is a way to transform this into a fractional version when we define a fractional normal. And the concept that emerges, which is called ES, a fractional version of this, does have an error estimate for assuming that we have a sort of a realistic regularity BV. Okay. Now, if you have prescribed mean curvature, meaning at this point, the curvature, the right-hand side of the problem is a function f, so we minimize this energy with a certain function f, we can see not only discontinuities at the boundary, the stickiness, but also discontinuities inside. So here, for instance, this is an f that is a sine function, so it's negative here, and it's, say, minus 0.1, minus 1.5, and in this part of the domain is actually 1.5. So the function f, the forcing, jumps at this point. And what you see is a discontinuity here and a discontinuity inside. You see the discontinuities. This is inside the domain. Okay? And the same happens in more dimensions. In here is an example in 2 dimensions where the domain is an L-shaped domain. And it's interesting. You see, a cut along this diagonal that you see here shows no stickiness in the convex corner, stickiness in the reentrant corner. This indicates a discontinuity of the solution. And then the solution goes on the other side of the diagonal to the corner, and there is no stickiness, so no discontinuity. So again, the convex corner or the concave corner play a very different role. This is not understood from the PDE point of view. I mean, people in PDE have not considered domains with this type of structure, but we can explore this computationally, and we have some explanation why this happens, okay? So again, reentrant corners lead to more stickiness than convex corners that lead to no stickiness. Okay, now let me conclude with the last couple of transparencies about the fractional P Laplacian. And the fractional P Laplacian is this problem where we have the weight here corresponding to the P Laplacian type. So P is equal to 2, this is no weight, and we have the Laplacian that I mentioned earlier. This is the Euler-Lagrange equation of this functional, where instead of the W1, 2 norm, we have the WS P norm, okay? Very much what I had before, except that now the exponent, the integrability 2 is replaced by integrability P. This is the weak formulation. Again, similar to what we had before, except that we have this weight that makes the problem quasi-linear. But you see, we have a functional that is very much like the F2 that I mentioned before, minus F1. Okay, so it's possible with the same trick that I mentioned earlier inspired by Savary to prove a best of regularity. And this best of regularity uses a slightly different technique. This is work in progress from the one that I mentioned earlier, and it's such that it improves upon what I had before. Okay, so this is the type of shift theorem that we can prove. Okay, we have a shift of S to S. We go from minus S plus something to S plus something. Now, gamma and gamma prime are kind of dual from each other. So this leads to this Sobolev regularity. And with this Sobolev regularity, we can prove error estimates. And here are the results. They are not important, they are technical. The point is that when P is equal to 2, these results improve upon what I just mentioned earlier. Okay, so this gives you a kind of quick tour on fractional diffusion, mostly linear, some hints to nonlinear stuff. So let me conclude. This is a summary of what I mentioned to you. I insisted on regularity because it's definitely important to understand approximability, but I also show you that the computations indicate that there are some regularity results, particularly regarding stickiness, that are not well understood. So it goes both ways. So I mentioned finite element methods, issues that had to do with implementation, compression, and solution with fast solvers. I mentioned several error estimates a priori, global and local, and quasi-linear problems. Two types, fractional minimal graphs and fractional P-Laplacians. Much more has to be done, particularly in the nonlinear context. Here are references of papers that are kind of recent, of the various topics I talk about. I didn't show much. Many of these results are technical, and here is a collection of papers. The last one in preparation that had to do with the P-Laplacian. And here are survey papers that kind of go over the various topics. And finally, here you see references to other people that have contributed in various aspects, regularity, for instance, for polygonal domains. Particularly this result here by this group is interesting because they were able to do very complicated estimates of analytic regularity, starting from our results of Bezo spaces. And again, error estimates of various types and fast solvers. And this is it. So I appreciate your attention. Thank you very much.
Many thanks, Ricardo, for the nice presentation, an overview on recent results on fractional diffusion. So there's time for questions or comments. Let me see if you can basically open the microphone and speaks directly or write in chat. So meanwhile, I would like to ask Ricardo a quick comment on a posteriori analysis for fractional diffusion.
I didn't say much. There is some work on a posteriori error analysis. There are several, not too many, but some papers. For instance, by Mellenc and his collaborators, there's some work by Ainsworth, but it's a little bit more practical, I would say. The most refined work that I know is by Mellenc and collaborators. And it's very complicated because the problem is that you cannot write the residuals in the usual form. And we are used to doing this for Laplacian operator when you get the residual integration by parts. But the operator here, when you apply it to piecewise linear functions, it would be the strong form of the residual, is very singular near the edges. And so you need to cope with that. And it's not obvious how to do it. I mean, Mellenc and collaborators have used weights to do that. I'm not particularly convinced that this is the best way to go, but this is a topic that is not fully understood, in my opinion, and I'm not sure that we are we have the most desirable estimators at the best possible results.
Thanks. Other questions or comments from the audience? So let me just add another. Oh, sorry, Andrea.
Yes, hi, Ricardo. Thanks for the very nice lecture, very clear. I was wondering, it doesn't look like, given you have full matrices and the type of regularities, one may think that standard finite elements is not the ideal type of space, and one could think of something more global, like some kind of radial basis, or is this something that has been looked for these problems?
There are people that I'm not sure about names. There are people that have looked into this. There is let me point to the following reference that has a lot of stuff, and there is a survey paper by Karniadakis and several collaborators. For instance, Ainsworth is one of the co-authors, where they look into fractional diffusion. I think the title of the paper is the survey is what is fractional diffusion. They talk about several different approaches. In particular, they talk about radial functions, and of course, you can also do other things. You can do finite differences. Why you want to do finite differences? They are not better than finite elements, in fact, and even for this problem, they are probably worse. But I'm not sure that we have that I can tell you for sure that the radial basis functions they have a room. I mean, I'm not in that particular area, so in that sense, I'm biased. And what I describe here is a biased view of fractional diffusion. I didn't describe every possible technique. In fact, to be fully honest, and I didn't say it in any detail, when you look at finite elements, there is a class of elements which I listed here, but I didn't discuss. I discussed other topics. I wanted to say something about nonlinear problems. These techniques called Dunford-Taylor methods were advocated and are advocated by Bonito and Pasiak and people working with them. So they are basically, they are ways to write the fractional problems in terms of full operators of order 2, and so to superposition of them in some proper way. It has to do with representations in the convex, in the complex plane. So contour integrals. These methods are very interesting. They have very interesting properties. They can be formulated in any dimension. So this is one avenue to 3D. For instance, and they are very good. They are you can precondition them very easily because they are basically Laplace type problems. So this is probably in my mind a better way if you want to go away from the formulation using the integrals, okay, these singular kernels. However, the problem with these techniques are they are very linear type of techniques. Once you move away from the linear regime, for instance, you enter the quasi-linear regime that I mentioned at the end of the talk. It's not clear what to do. So I didn't give you a full answer. I just gave you, aspects, various possibilities. I mean, I think that this is not clear.
Thanks.
Blanca.
Hola, Ricardo.
Ah, hola.
No, so I have 2 questions. You did a lot of work in the past using the Caffarelli-Silvestri extension and its finite element approximation.
Yeah.
How do you compare the two?
Okay. Okay, that's a good question. In fact, Caffarelli-Silvestri was only mentioned at the very beginning and ignored. Not because it's not important. I mean, it was certainly a very instrumental type of result. It was instrumental in my work because the first things that I did together with Otarola and Salgado was inspired by the work of Caffarelli and Silvestri. We did discrete versions, finite element method based on that extension. In our work, we were working, and we were driven by another formulation of the problem, which is called the spectral Laplacian.
Okay.
It's different from this integral Laplacian. The spectral Laplacian is basically, dealing with, the eigen decomposition of the usual Laplacian and scaling the eigenvalues with the power s. That is meaningful, but it has a different probabilistic interpretation. It has a probabilistic interpretation, but it's different from these jump processes that I mentioned. From the PD point of view, the boundary behavior is different. The problems, the fractional Laplacian with spectral Laplacian has a better boundary behavior. The boundary behavior of this integral Laplacian is worse. And in a sense, this is the type of operator that is most used in applications. That's why I did not mention the other one. The fractional Laplacian with a spectral operator is very reasonable in applications like phase transitions, for instance, when you really want to have a fractional operator inside the domain, but you don't care about a probabilistic interpretation. Or, for instance, in dealing with image processing. In those contexts, it's very natural even not to use finite elements, but rather use spectral methods.
Okay.
And so, the domains in those applications doesn't matter, so it's typically square. So spectral methods are the best way to go. And there are, if you want, I can give you references. So there is light and life for these operators, but I didn't focus at all on that.
Okay, and the second question is a follow-up on Marco's question. Cannot you use any of the results you obtained for the BPX to get an idea? I mean, because you use subspace correction in a way.
Yes.
To get some hints on how to get the a posteriori and the analysis there?
I don't know. I don't know. It's not something I didn't think that way. It may be. It may be because what I thought quite a bit about posteriori error analysis, but not in the context of subspace correction. It may well be an interesting avenue. Because I mean, the direct approach that I had in mind is very hard to implement. And in fact, Melink implemented it in a sense by using these weights. It's not a joke, okay? So I'm not sure. I mean, I don't have an answer, but it's an interesting proposition.
Anyway, thanks a lot for the very nice and very technical.
Thank you. Thank you for attending.
Are there any other questions or comments for Ricardo? Okay, so if not, we would like to thank Ricardo once again for his great talk. Thank you, Ricardo.
Thank you all.